Hey everybody, this is our last section in logic, and the name of the section is Euler Diagrams. This is a French name, and if I spoke French, I'd probably pronounce this correctly. I don't, so I slaughter it. Americans tend to pronounce this word Euler. I'm sure the French don't pronounce it anything like this. And when they hear this word pronounced Euler, they cringe. But I don't speak French and I don't know any better. So Americans who don't speak French pronounce it Euler. Hey, it's what we do. Now, what are Euler diagrams? They're the use of Venn diagrams in order to determine the validity of arguments that involve quantifiers. Venn diagrams, remember what they look like? For A and B, two sets. If A and B are disjoint, the Venn diagram looks like this. If A is a subset of B, then we have a Venn diagram that looks like this, with set A completely contained in set B. And if A and B just in general have elements in common, we draw the Venn diagram this way. So I think we remember that, but it's been about a week, maybe a week and a half since we did Venn diagrams. Now, quantifiers. Quantifiers, okay. Those are quantifiers. The word all, some, none, and typically we're working with statements such as all such and such are, or some such and such are, or some such and such are not, or maybe none are, or no such and such are. But we're working with statements like that. So maybe I can give a better example in just a second involving quantifiers. Here's an example of how we might see quantifiers used in arguments that involve Euler diagrams. All mothers are loving people. The quantifier all and the verb are. Some pitchers are left-handed. The quantifier some and the verb are. Some holidays are not federal holidays. The quantifier some are not. And no bicyclists are violinists. None are. So we use Euler diagrams, and it's a special use of Venn diagrams to determine the validity of arguments that involve quantifiers like all, some are not, none are. And we discuss our strategy in just a minute. I guess the first thing that we have to do is look at the different types of quantifiers and statements involving quantifiers and learn how to draw Venn diagrams that depict the situation. The statement all A's are B's essentially says that anything that is an A is also a B. So anything in the A circle is going to have to be in the B circle as well. The A circle being the set of all A's, the B circle being the set of all B's. Well, if all A's are B's, then the A circle, or the circle containing the A's, would have to be in the circle containing the B's. That doesn't sound too clear, does it? So let's use an example. All frogs are green. And we'll let F be the frog circle. And we'll let G be the circle containing things that are green. So F is the set of all frogs. G is the set of all green things. And here's our universe. And it says all frogs are green. So all frogs have to be contained in the green circle. Here's our green circle, the things that are green. And all frogs have to be contained inside it. So anything in this circle is a frog. And so if any frog has to be in this circle, so it's also contained in the green circle. All frogs are contained in the green circle, so they're also green. So this is how we show that all frogs are green. Let's see, what would be another one? Some A's are B's. So there's at least one A This is another way of saying that some A's are B's. Now, it may be the case that all A's are B's, but this is not saying that. It's just saying that at least some A's are B's. So, we're going to draw A and B like this. And at least one A has to be in the B circle. So here's 1A, it's in the A circle, but it's also in the B circle. That's how we draw that. Now let's look at an example. Some bicyclists are violinists. So B is the set of bicyclists, and V the set of violinists. Here's our universe. And remember what this is the same as saying. Some bicyclists are violinists. It's the same as saying at least one bicyclist is a violinist. So we draw the bicyclist circle, and we draw the circle for violinists. And at least one of the bicyclists has to be in the violinist circle. So we'll just draw a little square there. And at least one bicyclist is a violinist. So this is our Venn diagram to show that some are, or at least one is. Okay, here's another scenario. Some A's are not B's. And that's exactly the same thing as saying at least one A is not a B. So we draw our circle that represents the set of A's. We draw our circle that represents the set of B's. And they may have some elements in common, we don't know. But one thing's for sure, at least one A is not a B. So there's got to be at least one element in the A set that's not in the B set. So we have to draw it in the A circle, but not in the B circle. So here's one A that is not a B. Now let's look at an example. Some bicyclists are not violinists. So we have a B circle for bicyclists. We have a V circle for violinists. And to say that some are not is exactly the same as saying at least one is not. So we have the bicyclist circle, and we have the violinist circle. And this is our universe right here. Some bicyclists are not violinists. Another way of saying that, at least one bicyclist is not a violinist. So we have to take one of the bicyclists in the B circle and make sure that it's outside of the violinist circle. So here's a bicyclist. It's in the bicyclist circle, but it's not in the violinist circle, so it's not a violinist. One bicyclist is not a violinist. So let's see, we've done all A's are B's, some A's are B's, some A's are not B's. See, what does that leave? No A's are B's? Okay. We'll do that one next. This is the last scenario that we have to illustrate. No A's are B's. In other words, there does not exist an A that is also a B. So we have our A circle, and we draw our B circle And I think there's something wrong with this. We draw them so that they're overlapping, and that seems to indicate the possibility that maybe something's right in here. And if there's an element here, it's in the A circle, so it's an A, and it's in the B circle, so it's a B. If there's an element right here, this is an A that's also a B. But our scenario is that no A's are B's, or there does not exist an A that is a B. So for this scenario, we can't draw our circles overlapping. They have to be disjoint. So let's try that again and see if we can do it better this time. Here's our A circle. Here's our B circle. And we've drawn them disjoint, so they don't have any elements in common. Any element that's in set A has to be outside of set B. So no A can be a B. Now let's look at an example. So B is the bicyclist circle, and V is the violinist circle. And there's an equivalent way of saying this. There does not exist a bicyclist. That is also a violinist. There does not exist a bicyclist that is a violinist. So we draw our universe. And we draw our bicyclists. And our violinists, and we have to draw these sets separate. Any element in this set is a bicyclist, and the way we've drawn the diagram, no element in the bicyclist set can be in the violinist set because we've drawn them disjoint. So no bicyclist is a violinist. There does not exist a bicyclist that's in the violinist set. Now those are the scenarios involving quantifiers that we have to deal with. Now let's see if we can do an argument involving statements that involve quantifiers. And as we do, we'll outline what our strategy is going to be. This is an example from an earlier edition of the text. I put it up here because I always thought that this was kind of funny. Our argument is some desks are made of wood. All paper is made of wood. Therefore, some desks are made of paper. And remember what an argument is. It's a statement of the form, conjunction of the premises implies the conclusion. So our argument is of the form P1 and P2 implies the conclusion. And this argument is valid if this is true for all combinations of truth values for P1 and P2, or for all combinations of the truth values of the simple statements that make up this argument. So if this is necessarily true under all circumstances, the argument is valid. If we can find one case where this statement is false, the argument's invalid. And what is the only situation where we have an if-then being false? The only situation in which an if-then is false is if this part is true and this part is false, if we have a true implying a false. So here's what we do. We try to draw our Euler circles or our Euler diagram in such a way that the conjunction of the premises is true and the conclusion is false. If we can do that, then there's at least one combination of truth values of the simple statements that makes this argument false. On the other hand, if we try to draw our Euler diagram in such a way that the conjunction of the premises is true and the conclusion is false, and we can't do it, then there must be a reason why we can't do it. If we can't draw our diagram in such a way that we have true implying false, it must be because for all combinations of truth values that make up the simple statements in this argument, we never have a true implying a false. The argument is always true. So here's our strategy again. Construct the diagram in such a way that the conjunction of the premises and I put conjunction of in words because drawing the diagram in such a way that the conjunction of the premises is true is exactly the same thing as drawing the diagram in such a way that each of the premises is true. See, remember, the only way a conjunction can be true is if both of the individual statements that make it up are true. So we construct the diagram in such a way that the premises are true, and two, then try to draw the diagram in such a way that the conclusion is false. If we succeed, then we have the conjunction of the premises, which are true, implying the conclusion, which is false, and the statement is false. So for at least one set of truth values, the statement is false, and the argument is invalid. Why? Because it's not a tautology. Now that's if we succeed. If we succeed in making the premises true and the conclusion false, then our argument is false for at least one set of the truth values that make up the argument. It's not a tautology. This argument is invalid. But suppose we don't succeed. If we don't succeed in making the conjunction of the premises true and the conclusion false, so we have a true implying a false, if there are no cases in which this happens, then in this case, the statement P1 and P2 implies the conclusion is a tautology. And the argument is valid. So that's our strategy. Just look at that for a few seconds before I erase it. Okay. Let's tackle this thing. Now, let's see. We have desks, we have things made of wood, and we have things made of paper. So D is our desk circle. W is our wood circle, things made of wood. And P, things made of paper. And we want P1 and P2 to be true. And yet we also want the conclusion to be false if possible. But we definitely will draw the premises so that they're true. Here's our Euler diagram. This is our universe. Now, all paper is made of wood. There's only one way that we can draw that, the paper circle has to be inside the wood circle. So we have the premise 2 satisfied. Now let's see. Some desks are made of wood, so we have to have the desk circle intersecting the wood circle. But at the same time, we want the conclusion to be false. So let's see, I could draw premise 1 this way. Here's my desk circle. And premise 1 is true because I have some desks made of wood. The desk circle and the wood circle overlap. So I have some desks made of wood. So there's at least one desk that's in here. Now there may be a desk in here also, which would mean that my desk is in the paper circle and I have my desk made of paper. So if I draw the diagram like this, my conclusion is true. I don't want to do that if I can help it. So maybe I don't want to draw my desk circle this way. Because if I draw it this way, there's a desk here, something in the D circle that's also in the P circle. This is a desk that's made of paper. I want to draw P1 so that it's true, but I also want the conclusion to be false. So let me try it again. The desk circle has to intersect the wood circle. Some desks are made of wood, but I want this to be false. So I don't want the desk circle to intersect the paper circle. So maybe I can do it like this. Here's my desk circle. And let's see. Here's one desk made of wood. So, premise 1 is true. And all paper is made of wood. My paper circle is inside the wood circle. So all things paper are made of wood. I have premise 2 satisfied. Now, what about the conclusion? The way I've drawn this diagram, is the conclusion true? Do I have some desks are made of paper? Ooh. The desk circle and the paper circle are disjoint. So the conclusion is false. So I have P1 and P2 true. And my conclusion is false because no desks are made of paper. The desk circle, no desk in the desk circle is also in the paper circle. So no desks are made of paper. So what does this tell us? Since we are able to draw the diagram in such a way that the conjunction of the premises is true and the conclusion is false, the argument is invalid. Let's do one or two more of these. Now, here's a good one. And I guess maybe I should write the instructions. Determine the validity of the argument. Okay. So our first premise, all Republicans drink coffee. The second premise, all Democrats drink coffee. Our conclusion, some Republicans are Democrats. So let's see if this argument is valid or not. We have R, the set of Republicans. We have D, the set of Democrats. Let's see, Republicans, Democrats, and C, the coffee drinkers. And let's see how we're going to approach this. Our strategy is the same. We try to draw the diagram in such a way that all of the premises are true, and if possible, have the conclusion be false. Here's our universe, and all Republicans drink coffee, so the Republicans have to be in the coffee circle. And the Democrats, all Democrats drink coffee, the Democrats have to be in the coffee circle, because we're drawing our diagrams so that the premises are true. So here's our coffee circle right here. And the first premise, all Republicans drink coffee. Okay. So that means that the Republicans have to be inside the coffee circle. Now, we also want to draw the diagram so that the second premise is true. All Democrats drink coffee. But we need to be careful. We're trying to do two things. We're trying to draw premise 2 so that it's true, but at the same time have the conclusion be false. Well, if the conclusion is true, some Republicans are Democrats, that means that the Republican circle and the Democrat circle have to overlap, because there's got to be at least one Republican that's a Democrat if the conclusion is true. But we don't want the conclusion to be true, do we? We want it to be false, which means that we have to draw the Republican circle and the Democrat circle to be disjoint. So can I get my Democrat circle inside the coffee circle and still have the Republicans and Democrats disjoint? I think I can. I think I can put my Democrat circle right here. Whoops. Democrats. Okay. The Republicans are inside the coffee circle. So all Republicans drink coffee. That's true. The Democrats are inside the coffee circle. So all Democrats drink coffee. That's true. So we have P1 and P2 true. Now, is my conclusion false? It is, because the Republican circle and the Democrat circle don't intersect. There are no Republicans that are Democrats, not even one. In order for at least one Republican to be a Democrat, that Republican would have to be in this circle and this circle at the same time. That can't happen. So our conclusion is false, and our argument is invalid. We can draw the diagram in such a way that the conjunction of the premises is true and the conclusion is false. Okay, let's do one more. How about this one? All singers are rich. Some poor people are singers. Therefore, some poor people are rich. Determine the validity of the argument. Well, I think we know how this is going to end up. But let's go through it. Let's see. S for singers. So S is the set of all singers. R is the set of all rich people. And I guess we have poor people, so P, the set of all poor people. Do we have anybody else? We got poor, we got rich, we got singers. I think that's it. Okay. And our strategy again, draw the diagram in such a way that the premises are true. But if at all possible, draw the premises so that the conclusion is false. But first and foremost, we have to draw the premises so that they're true. But we try to do it in such a way that the conclusion will be false. If we can do that, then the argument is false. If we can't do that, if we draw the premises so that they're true, and that forces us to draw the conclusion such that it's true, it means that the argument is valid. So let's get this show on the road here. Here's our universe. And let's see, U for universe. All singers are rich. So I guess we have the rich circle. And all singers are inside this rich circle. So here's our singers. And all singers are inside the rich circle, so all singers are rich. We've drawn this so that the first premise is true. Now, we want to draw the second premise so that it's true, but at the same time, we want the conclusion to be false. Let's see, some poor people are singers. So that means that the poor circle and the singer circle have to overlap like this. So here's our poor circle. And here, at least one poor person is a singer. Now, I think our hand is forced. I think this is really the only way that we can draw the poor people circle. It has to intersect with the singer circle. There has to be at least one person in the poor person circle that's also in the singer circle. At least one poor person is a singer. Okay. And now we want to do this so that the conclusion is false. Some poor people are rich. How do we make this false? This is false if no poor people are rich. In other words, the poor person's circle and the rich person's circle are disjoint. But, oh, look here. Here's a poor person, and they're inside the rich circle, aren't they? And that was the only way that we could draw it. We had to draw it this way so that the singer circle and the poor person's circle had at least one element in common. And when we did that, this poor person winds up in the rich circle. Ooh. So we drew P1 and P2 true, but we found out something. In order for P1 and P2 to be true, we have to have at least one poor person inside the rich circle. So in order for P1 and P2 to be true, Q has to equal true also. Since it's impossible to make the conjunction of the premises true and have the conclusion be false, this argument is valid. That argument is valid. And now you're looking at this and you're saying, wait a minute. Some poor people are rich? That doesn't make any sense. This statement contradicts itself. How can this be a valid argument? And I'll tell you why it's a valid argument, even though the conclusion is obviously false. the argument is based on at least one false premise, maybe two. This premise is false. It's not necessarily true that all singers are rich. So at least one of the premises is false. This premise is false. And it may be that both of them are false. Is it necessarily true that there are some poor people who are singers? Well, that's probably true. But the first premise is false. It is not true that all singers are rich. The argument is true. The argument is valid, but we get this conclusion that's obviously false because the argument is based on a false premise.